Oh, sure, no problem. So I'm Sean. I manage the Rideshare Labs team at Lyft. I previously had a PhD from NYU in information systems. A lot of my early work as an academic was in social influence, pure effects. So I used to work on sort of like hard causal problems in the social science domain. After grad school, I went and worked on Facebook's core data science team, where my focus shifted to working on experimentation as a very natural sort of like way to answer some of the causal questions that were quite hard in the academic world. 2 years ago or so, I switched from Facebook to working at Lyft, where I was exposed to like a broad new array of business problems. I think Lyft has been sort of very instructive for me about running an efficient business. We have a very like hard to monetize, or it's an easy to monetize product, but hard to make profitable product. So efficiency and making good decisions is the whole business. And so it's been very exciting to sort of like try to apply the causal inference lens to all the problems at Lyft. So I'm really excited to talk about that today. Let me get my slides queued up. I think my Zoom newbiness is gonna, here we go. And I wanna do everybody can see the slides? Can I get a confirmation? Great. All right, the title here is meant to be pretty provocative, I think. And it's because I think like, you'll hear some hardcore causal inference people kind of pejoratively call machine learning curve fitting. And as I was reflecting on what I spend a lot of my time at work doing, it's actually like looking at curves that we fit that are helping explain some variation and some effect. And as I thought about it more, a lot of what we do is curve fitting, and it's actually quite reasonable to think about the task that we have at hand as curve fitting because of how experimentation driven we are. And I'll try to explain what that means a little bit as we go. So my goal today is to kind of give you a tour of some causal inference problems at Lyft and try to help you understand why machine learning and experimentation are really at the core of what we're doing. So just to give you a sense of like what my role is like, I work in this matching capacity is the way that I think about it. So I talk to and work with many scientists at Lyft. We have a ton of talented people from a number of different backgrounds, and they work on all aspects of the business. And I try to understand what their applications are. So what problem are you trying to solve? What kind of estimate would you need to solve that problem in a better way? And in a way, I've been sort of clustering these themes in my head for a long time. At the same time, I try to stay in touch with the academic community and try to understand what methods are being developed, what the latest and greatest methodologies that we have available. And then this is kind of like me at the intersection here, performing some matching role, trying to understand like whether there are methods that can apply to applications. Sometimes I'll actually send the applications over to methods researchers and do the opposite kind of matching. And this is a very high bandwidth area. So it's sort of like there's lots of applications being developed, lots of methods being developed. So I find my attention is spread pretty thin these days. But I hope today to kind of give you a sense of like what I'm doing in this matching role at Lyft, and sort of maybe that will help you understand some of the themes of methods that we found particularly useful, and also some of the applications that we tend to work on. So just to summarize what I think are some of the conclusions in advance, in a business setting where we can intervene programmatically, confounding is much less problematic than it is in the academic world. Most of the causal questions that we have are things that we can answer directly with experiments. So we don't end up in a world where we have a lot of problems of like, oh, we need to draw a DAG and figure out if it's identifiable. I think often we sort of like know how we can learn what we need to learn, and we do it through interventions. Doing that smartly is, I think, an important part of it. A second theme is that it's not enough to have estimated something. It's not enough to have a parameter estimate or a model. We have to automate decisions. We can't run the business through a bunch of manual analyses. We have to actually have some formal models and some code that executes them and uses them in order to make decisions on a very like high frequency basis. The third theme is that once you start automating decisions, that you need to clearly define goals and trade-offs. And this is really important and difficult, and it's something that we sort of like have a hard time doing. But if you don't do it correctly, then you optimize the wrong thing. And so we're going to like go to all this work to fit the best models that we can, and then make the wrong trade-offs. It's sort of like kind of a poetic way to do poorly. And then finally, this is the curve fitting part, is that you'll see throughout the entire talk that predictive modeling is the thing that really drives the value in a lot of ways. In a few different themes pop up there. One is that understanding effect heterogeneity is a big theme for efficiency for us. Second one is that reducing variance of models that we produce helps give us more precise answers to what we should do. So either through estimating the future states of the world better in a forecasting context, or through like reducing uncertainty in the effects of certain policies, measurements of the effects of certain policies that we're executing. And then finally, like predictive modeling helps us pool information across policies and like build up a model that kind of accumulates knowledge over time. So I want to start with a very simple example, and I think it's kind of like illustrative of some of the problems that come up at Lyft. It's highly simplified, but I'll talk you through this. This is a DAG of like, say, a day at Lyft. And so we have some drivers who are going to decide to drive that day. So there can be more or less of them depending on how interested drivers are in driving. Sessions are what we call like when a user opens the app and decides to maybe take a ride. So they're checking a price, entering a destination. We call that a session. So more sessions is how we would measure demand. So how many people are looking and potentially requesting rides. These two things combined produce rides. So more sessions usually produces more rides. More drivers will produce more rides. If people have a really good experience because we have enough drivers, they might decide to use Lyft in the future. And then rides per driver might be some way that we measure like utilization of drivers. So how hard are the drivers working that day? And then finally, we have this incentives piece. This is our interventional node. We get to set this variable, and this is important. Sort of like why we have a problem is that we have a choice here to make of like how much we're going to spend on driver incentives. So highly simplified problem, but in a lot of ways, the Lyft business is all about getting the appropriate value of drivers, the appropriate amount of drivers into the setting that we want in order to maximize some outcomes that we might care about. So here's our lever. It's a function of incentives. So and we can kind of like maybe make some kind of like conclusions about what this lever might look like. This lever in particular is just incentives causing incremental drivers. Levers are actually like quite common in business, just sort of like the idea that you could spend money on something and get some intermediate output. And it's usually the y-axis is not like the business goal itself. It's something that contributes to the business goal in some way. And so we have to figure out some way to value that in some second model. A lever model is a curve. It's a curve where as we spend more money, we get more incremental something. And driver incentives are just one example of this. So we might spend money on giving coupons to riders. This would improve demand. But even programs like, hey, we could send staff and hire people to work at airports to help people use the Lyft app and get Lyft rides at the airport. And this would be an expensive program, but there might be high incrementality if we do it at the right times and places. Even like a car maintenance program where we say offer drivers like a steep discount on keeping their cars in good shape would be something that could like improve the rider experience in some way, or decrease the probability of a driver getting into an accident. And we can spend money on that, and there would be some incremental benefit of that we would want to estimate. And so a theme about levers is that they all sort of have this diminishing marginal returns sort of shape to them. And this is a causal model. So we'd like to sort of interpret it as we spend more of this or less of this, that we get this intermediate outcome. So how do we understand, where does a lever come from? Often there's just sort of some costly treatment that we'd like to deploy. Incentives are a great example because it's just we're directly spending money as a bonus to drivers if they happen to drive that day. And so what we use in order to deploy costly incentives is very standard in the literature, heterogeneous treatment effect models. So here I'm kind of compressing this curve into one dimension, but it may be more. But say we had some pre-treatment covariate that we thought was predictive of both likelihood of driving and also response to treatment. We might build a model like this, and this model is now two curves a curve of likelihood of driving for certain drivers under a no incentive situation and likelihood of driving under an incentivized situation. And the difference between these two curves is what we would call incrementality. So like how incremental is the incentive. So these drivers out here are likely to drive even without incentives, and the incentives are only very small in their effects. These drivers over here are very unlikely to drive, but with incentives would be likely to drive. And so these are high incrementality drivers. And so that curve, that diminishing marginal returns curve that I showed you on the previous slide, is just sort of like walking down the set of most incremental drivers to least incremental drivers and deploying incentives in some way that maximizes efficiency. So drivers themselves are not the goal, and so that causal model is incomplete, and it doesn't give us a way to make decisions about what we should actually do. So we need this second phase of the model in order to do this. We call this a production function. A production function is a thing that takes intermediate outputs and produces an output that we really value. So here in this case, it's rides. So I'm just sort of like making a stylized argument. Rides might be what we would choose to maximize. It's not actually what we choose to maximize, but it could be. So this function f sub r is a production function. It's telling us, like, given the amount of drivers and sessions that we have on a particular day, or supply and demand conditions, what kinds of outcomes are we likely to see in the marketplace. Production functions are also just curves, and estimating this curve, better or worse, is going to influence the decision quality that we happen to make. It's just that this curve is now two-dimensional. Here are three different demand scenarios. So if we had a very small amount of demand, then each incremental driver would be pretty not incremental to the amount of rides that we produce. Whereas if we're in a high demand situation, having more drivers can produce a lot of rides very efficiently. So this is a case where the context really matters, and knowing what state of the world we're in with respect to sessions is an important part of the problem. Also, just measuring this incrementality on this curve is sort of what's important as well. So when we're ultimately making this decision, we're going to say, hey, we can produce drivers with a certain cost, and then those drivers are going to produce rides with a certain efficiency, and so we're going to get sort of like the multiple of these two things. I will mention that production function is quite challenging to estimate. This is one case where confounding is a challenge because we don't have very strong instruments here. Like the levers themselves do shift drivers, but the marketplace outcomes are quite noisy. So it's a case where variance is a real problem for us. Let me give you a flavor of how we think about estimating a production function. We can treat it as a predictive modeling problem where we have like some predictive loss. Like we'd like to predict rides given some historical amount of sessions and drivers. And this would match empirical predictions, but it wouldn't have any causal interpretation. We also know something about the shape of the function because there's some economic theory that can help guide it. We know that we're going to get diminishing marginal returns to additional drivers and additional sessions. So we can penalize the function that we're fitting in order to impose some assumptions about the shape in the case where we have sparse data. And then finally, we have other sources of evidence about what we would call the incrementality of additional drivers. And then so what we can do is impose what we call replication loss. So here's an example of like that playing out in practice, and I'm not going to show you what the actual X and Y axes are here, but here are two-dimensional curves. Fit to data. And then this dot with the green line is an experimental result. So from some experimental evidence that we have. And so what we're doing is we're regularizing the curve, the slope of the curve to match the slope of the experiments. And so this is just sort of a straightforward way to sort of like use the model to predict counterfactuals and then penalize the model for disagreeing with this other source of causal knowledge that you have. And so this allows us to sort of like fit something that looks like a predictive model, but just has another regularizer that helps give it a more causal interpretation. I won't go into too much more detail about this. This is still sort of like not a completely solved problem, but this is a helpful approach in that it allows you to pool information across multiple sources of causal evidence. Finally, we made it through the production function. Now I'd like to talk about the outcomes. I put them here on purpose because these are trade-offs that we make. So we know that having a good marketplace experience with tons of drivers, those people will not have to wait very long. So they might end up sort of using Lyft more in the future. And that would be something that we'd like to care about as well. So caring about rides today might be kind of greedy. Caring about sessions in the future might be better. So it's sort of like, oh, this is, most of the business is happening in the long term, not today. And so we want to kind of like put this into our utility function. We also care about whether drivers are earning enough. And so having very few number of rides per driver would be a bad marketplace outcome for drivers. They might be less likely to use the platform in the future. And so this is another outcome that we might care about. So we have at least 3 sources of value to the business, like today, tomorrow, and the driver-rider split. Drivers would prefer us to not improve the number of drivers in a lot of cases because they would be more occupied and make more money per hour. So again, these trade-offs, understanding them requires estimating curves again. And so here we have examples of 2 of those curves. Here for long-term effects, it's another 2-dimensional curve. So as we increase the number of drivers, we'll get some future sessions at some point in the future. And this is a thing that this is an object that we'd like to estimate in order to effectively make the short-term, long-term trade-off. And then driver welfare might be captured by rides per drivers, and it's sort of like increasing at first, but then decreasing as we add too many drivers to the marketplace, and it becomes saturated. And so we need to weigh like the short term, the long term, and this driver welfare in order to effectively make this decision. And if we sort of neglected any one of these particular outcomes in our causal model, then we had poor estimates of any one of these things and the effects of them, then we would make a sort of suboptimal decision for the global objective of the business. So what are we actually trying to do here at the end of the day is like we're trying to do some optimization. So here's a kind of simplified statement of the optimization that we're trying to solve. And you can see that the inputs to this optimization are all kind of like causal quantities of interest, in this case curves, or in this case sort of like some exogenous state. We're going to maximize, we're going to choose the optimal level of incentives, and the incentives will cause a certain amount of drivers to appear in the marketplace. We'll have some exogenous amount of sessions, and then through those we'll end up with some estimated amount of rides. And then there's some value per ride, alpha, that puts it on a money metric scale, and then we're going to subtract incentives from it, and we're going to end up with our optimization problem. So you can see like directly from this optimization problem, we have 6 possible ways to improve our outcome. Three of those ways are from improving the ground truth. 3 of those ways are from improving our estimation. So in the case of ground truth, it's quite simple. We need new programs or better ways of deploying incentives. In the case of demand, we just need luck. We need the people to show up. We have other levers for doing this, but in this model, there's no other cause that we can use to improve the state. In the case of the production function, we need a better marketplace, and I'll talk about that in the next couple slides. And then these other 3 problems are statistical problems, where like if we have a bad estimate of the heterogeneous treatment effects of incentives, where that model is not calibrated appropriately, then our cost curve estimate would be wrong, and we would be making an inefficient allocation. Say we were like overly optimistic about the effects of incentives, we might spend too much on them. If we had a bad forecast of demand, we can make a catastrophically wrong decision. So like if demand is likely to be high and we underinvest in incentivizing drivers, then we could have left a lot of potential rides on the table. And conversely, if sessions were really low and we spent a lot of money on incentives and those drivers showed up and had nothing to do, that would be bad as well. So forecasting becomes a key component here. And then finally, estimating that production function better is sort of like an ongoing project at Lyft. I think like as we get better estimates of our production function, we can solve this problem more efficiently. So those 6 sources of value, I think straightforwardly translate into some data science tasks that we tend to work on at Lyft. And actually, I made this slide a few days ago, and as I was making it, this is sort of like a great summary of some of the work that my team does. So we have a forecasting and planning pod that works on improving our forecasts as inputs to decision making. And forecasts are important because we have to make that incentive decision in advance. We can't just incentivize the drivers in real time. We have to give them some lead time in order to say like, today's the day you should show up and drive because we think we'll have a lot of demand. So knowing these advanced conditions improves the state, improves where we end up from an optimization standpoint. And what's interesting about the forecast is that they themselves can be causal models because, say, demand might depend on how much we spent on coupons in the last week. And so we would want to incorporate that into the forecast. So our forecasts are, in fact, causal models and need to have that causality baked into them in order to have some prediction of like what's happening given what we're choosing to do over the historical data. On the lever side, we're making pretty large investments in heterogeneous treatment effect models that can help sort of identify more heterogeneity in the population and help shift this curve outwards. For a given amount of incentives, we can produce more incremental drivers. That would be like a free efficiency just from a better model, sort of like a rare thing. But if the model can get better and just directly shift this curve outward, that can be great. Another way to do this is just by designing a better, more persuasive or valuable offer for drivers that would also shift the curve upward. So this is like, these are both ground truth changes, but they also translate directly into value for the company in some in some like dollar terms. Finally, probably the most exciting thing in a lot of ways is like, what if we could improve the production function, and for a certain amount of drivers and session state of the world, we end up with more rides. This is the dream, is that we can just, by making better decisions about how to match drivers and riders on an ongoing basis, we can just generate more value by creating a more efficient marketplace. And it's the most high upside thing that we can work on, and also the riskiest, and that it's just very difficult to improve it. And so for the rest of the talk, I'm going to talk about improving the production function and the challenges that we face here and how we think about that problem. So in the marketplace, it's a little different than the setup I just gave you, in that there's not just one lever, there's algorithms that run, and we don't have to make a single continuous choice. We need to make a sequence of ongoing choices. So I'm gonna use the word policy to describe choices that we make through algorithms on an ongoing basis. And so like you'll see it used quite generally, but in this case, policy are causes that we directly control. I'm going to use diagrams like this quite often for the rest of the talk, and I want to just kind of familiarize you with what I'm looking at here. So the x-axis is usually time, sort of like showing the progression of time in the marketplace. The y-axis is space, and I know space is two-dimensional, but it's totally reasonable to compress it into one dimension for visualization purposes. And so things that are far away on the y-axis are far away in physical space, and things that are far away in the x-axis are far away in time. And so what's this first visualization showing is a driver's here, and he's sitting still. He's not driving anywhere, and he's just sort of like hanging out, and he doesn't have any passengers yet. So how does the marketplace function? Well, we have some supply and some demand shows up. Two riders at the exact same time, but not too close to the driver, are both making checking to see if they would like to take the lift. And now we have our first algorithm enters the picture. Is we need to make an estimate of how long it would take this driver to get to this location. We call this an ETA. And so we have a model in the system that's kind of like able to answer questions about how long would it take this driver to get to this particular location. Some people might think of this model as just a pure predictive model, but in some sense it is a causal model, in that we're sort of saying like, if we were to send the driver on that route, how long would it take? And so there is sort of like some sense in which there can be some confounding, particularly from the training data that we happen to train the model on, but I don't have time to go into that today. But this is actually a very interesting model in its own right, but we'll just treat it as a black box that can tell us like how long, how far the distance is in time terms. So next, these sessions are waiting for, the user has some time to decide whether they want to make a request. And they make that request based on whether the ETA is low enough and whether the price is low enough. So a highly simplified model of user behavior at Lyft is that low ETAs and low price cause them to take rides or make requests for rides. And so that session can convert into a request. And so this is our second algorithm. It's basically a function of the session properties, say like the origin, the destination, the time they're making the request. We will choose a price. The price is going to determine whether they make a request. And now we have our third policy, which is we're going to score each one of these requests with respect to this driver and give them a score. And then the request with the larger score is going to get picked up. And so here we made a binary decision in this case because we just happened to have 2 sessions. But if we had had 3, we would have taken the top ranked score. And if we had 2 drivers, then we would have allocated them using some integer programming system. So we're basically deciding based on the scores, what's the optimal allocation matrix between the set of drivers and the set of requests that we have available. That's our dispatch algorithm. But really at the end of the day, you can think of it as just a score function that's valuing like the match value between a particular driver and a request. So these 3 functions are our algorithm, and they operate at a particular point in space and time, and we're using them to make all the decisions. So in a way, the whole Lyft marketplace is just the sum total of a well-made set of these 3 decisions that we're making. And so like at the end of the day, this is what drives all of the outcomes for us. So how do we improve marketplace efficiency? Well, we have these 3 mechanisms. We can improve any one of these 3 functions that we have. These functions are pretty well defined. And so they convert into efficiency in different ways. So in the case of ETA prediction, if we make fewer mistakes on how long it's going to take a driver to get somewhere, then we'll make better dispatch choices. So we won't send a driver somewhere that it would take them too long to go to. Or if there's a rider really close, we could sort of recognize that better and make sure that that rider has a better experience. So this is a key input to all those decisions. Pricing is a very important policy for us because it controls, we call it shedding demand, where if you increase prices, people make fewer requests. This can be desirable in some settings where you don't have a lot of supply. It can be undesirable in settings where people are paying too high a price and you have a lot of drivers sitting idle. And so in a lot of ways, pricing is sort of like a way to control supply, demand, and balance. So we have a system called adaptive pricing, and that adaptive pricing's goal is to sort of like moderate the supply and demand balance. And then finally, we can change our dispatch scoring systems. So how do we score the match value between a driver and a request? The simplest version of this could just be ETA. So like the short, in that case, it's kind of a greedy algorithm that would always take the driver that's closest to the request and route them there. There are other ways to change this algorithm that might make more efficient allocation. So an example for like would be maybe we wait a minute or 2, and so we can, and then in the scoring function, we sort of like provide a penalty for like the request being too soon. And then we might say wait for additional requests to come in, and we might find one that's a better match. And so like rescoring is an example of how we might modify this algorithm in order to do a better job. So we have these 3 different kinds of interventions. The way that we test interventions like this is what we call a switchback design. Switchback designs are, or we call them time split tests, are basically just turning an algorithm on or off. And they can be represented very simply as just sort of like a square wave. So here's an example of like, we switched it on, then we left it on for a few hours, turned it off. And then we left it off for a few hours, and we turned it on, and so forth. This is a kind of an example of what some folks will call an N of 1 trial. So we have just one unit of analysis here, and it's an entire geographic region. And why do we do this? Is because we expect that the algorithm changes to have interference issues across space. And so switching an algorithm on for just some people or just some places would have spillovers that would affect neighboring places. And so by discretizing it into regions where we expect the effect to be concentrated, we get these sort of like, we get to ignore interference issues, but our experimental design becomes more complicated because we only have the ability to change the treatment status within time and not within units. How do we actually design experiments like this? Currently, the most efficient design that we have is a block randomized design. And so the idea here is that we would like to achieve some covariate balance across time and space, or across time. And the way that we do that is we take, here are days of the week, Monday, Tuesday, Wednesday, Thursday, Friday. I didn't fill in treatment status for these other days. Let's say on Monday, the first half of the day is in treatment, the second half of the day is control. So we flipped a coin to determine which of the 2 periods is going to get the treated status. The following day, we flip a coin again, another independent coin. This is for the first week. In the second week, we invert that decision. So whatever randomization played out the first week, we invert that randomization. We call this reflection. And what this is doing is achieving sort of a natural comparison group for this block can be compared to this block or to the neighboring block. And so we get some balance across local time and also across like intra-week and intra-day dynamics. And so this is giving us sort of like a more efficient estimator. These tests that we're running are just what I would call like a special case of space-time treatments. In a space-time treatment, we go back to this x-axis of time and y-axis of space. And we have these periods of treatment status and periods of control status. And so it's basically like a mapping from space and time into some treatment. And we get to choose this treatment status directly. It's exogenous to all the market outcomes. So it's a cause. It's a root node or a parent node in the causal graph. We have complete control over it, and so we can assign it. And this is a very powerful idea, and space-time treatments will generalize, as we'll see. So how do we look at the effect of a treatment that's designed like this? Well, actually, it's kind of like a signal processing problem in some ways. So we can think of the square wave that we're generating through varying our policy as a treatment wave, and then we have some convolution that we're convolving that wave with in order to achieve some outcome. This is what we would observe from the process, minus the noise. And so like our policy decision here is this treatment variable. This delta is the convolution, which is sort of like the timing with which the effects occur, and how large they are, what their sign is. And this is our object of estimation. We'd like to know what delta is here. And what we observe is y sub t, and then with some noise added to it. So this is like a way of thinking about our causes and our effects. Is the causes are input waves, the outputs are some convolution on that wave that we observe with some noise. Sorry, I know I'm getting some questions, but I think I'm just going to try to wait until the end to get through them to make sure I have enough time. So what do the effects look like now? We can kind of like plot them with color on top of the treatment status. So here are some colored blocks showing sort of like some accumulated treatment effect over time, culminating in some large effect, which is the darker region. And the effect could last longer than the treatment period in some ways. And so this would cause potentially some interference across time, meaning that the control period here would have a bias estimate of its outcome because it's sort of including some of the effect from the previous period. This little overlap here we often call burn-in. So when we're running an experiment like this, we might choose to discard, say, the first 30 minutes or first hour of the block because we think that some of the treatment effect has accumulated. Why would effects accumulate over time like this? You can think of it as that the algorithm is setting up the state of the world in a different way that needs to be accounted for. So say we will reposition drivers or shed too much demand or something like that. So a very aggressive price increase during here could cause a lot of riders to say not take ride requests, and so that would spill over into the next period. So there's lots of ways in which things can spill over in time, and we need to be able to account for that. When the effects of a treatment are very long-term and we're worried about them sort of having a very long convolution, then we have to run what we call region split tests, where we do the unit of randomization as our whole regions, we call treated regions, and then we have some control regions that we use as the counterfactuals. And here we're just switching the experiment on and leaving it on. And so this is almost like a launch. And we're just retaining some control regions in order to estimate some counterfactual. And so for this sort of setup, it's very popular to use synthetic control methods. And it's actually very clear from this diagram what we're doing with synthetic control methods, which is sort of like take this treated time and space and discard this information and use these three blocks of data in order to infer what happened in this time and space. This is another curve that we're fitting. And just to make the curve analogy clearer, like this is a curve that we're fitting. This would be another curve that we're fitting, would be the effect of this, this colored region right here would be another curve. just kind of like project it into a color dimension. We can generalize the space-time treatments even further. So here's an example of a product that we have. It's called a power zone, and so power zone is a time and space where we create incentives for drivers to drive to that space. And the reason is that if we know we have a lot of demand coming in a particular region, we'd like the drivers to be nearby, and that can be efficient. We call this like driver repositioning. How do we represent this treatment graphically? It's a rectangle. So there's a space under which the treatment is being applied, and there's a duration, a time under which it's being applied. And then the effects here are this sort of like trapezoid shape. You think about like, I just drew this trapezoid shape arbitrarily, but you can kind of like reason why it should look like this. It's sort of, we expect some bleeding over time. We're like, we migrated a lot of drivers to this region, so it might help improve marketplace conditions after this treatment is over. It also can create some benefits or maybe costs in space. So say like the drivers come from here to here, maybe there are some benefits to some areas neighboring here. Maybe there are some costs to some neighboring regions because we actually take drivers who are very close by and move them only into this incentivized space. So there's lots of ways in which the effect of this treatment can sort of spill over into space and spill over into time. And then taking this even further, we can think conceptually about treatments that we don't control, but have very hyperlocal, that are very hyperlocal. So going back to our driver position plot, so drivers are driving along, they pick up either passenger 1 or 2, and we're making a decision there. And then this passenger gets dropped off here at this point in space. And then this passenger gets dropped off a much longer ride, almost twice the length, at this very different point in space. These drop-offs are going to increment the supply conditions in that particular time and space. So riders who have ride requests nearby here are going to enjoy a shorter pickup time as a result of these drop-off decisions that we've made. So this dispatch decision causes drop-offs, which cause these space-time treatments to occur. And then there are effects here that are localized to that particular time and space where that driver becomes available for pickups in a particular region, a particular geographic area. And so this might be like a causal effect that we'd like to estimate in order to make a more effective dispatch decision, or we trade off, say, length of ride and drop-off location in order to make a more optimal dispatch decision for the marketplace. And I just want to make the point that at Lyft, these space-time treatments are almost everything that we care about. If we think about what a user level randomization would do at Lyft, let's say we did like a 10% test at the driver level or the rider level. This is what it would look like at the rider level. It's just people's ride intents, or sorry, sessions would pop up certain places and times, and we would end up with lots of points spread out in relatively uncontrolled ways, and we wouldn't get any clustering of the treatment into any particular places where we could get a strong enough effect. So this would just dilute the effect and cause tons of interference problems. And so a user level randomization is just sort of like not particularly useful in a two-sided marketplace that has some geography for it. How can we model space and time effects? We talked about the one-dimensional convolution a few minutes ago. There's also a three-dimensional convolution that's just a generalization of that. So if we think about our policy tensor or treatment tensor as having like a latitude, a longitude, and a time dimension, it's just sort of like a three-dimensional array of treatment status. And then we have this convolution, which is a three-dimensional cube of weights. And you could think of these as like an influence of this policy value over the observation value. And this is a very common in the convolution, neural networks literature. This is a convolutional neural network. So we're trying to learn a convolution that explains the observations that we occur. So the convolution is the effect, and it determines like where in time and space the effect is concentrated. The policy determines what policy or what the cause is. So the cause convolved with the effect gives us the observations. The convolution should have certain properties. So it's asymmetric in time. Because it's causal, we should not see things that happen before treatment having any effects, but after treatment they can, and they would tend to decay in most cases. And then similarly in space, we should see sort of like a treatments that are local to a particular observation should have a stronger weight. So kind of like an interesting, this convolution is a curve that we're fitting in order to explain what the effects of our policies are in a time and space dependent way. Another kind of curve that comes up quite frequently for us is that we'd like to have some baseline model of the system. So we talked about this kind of like convolution. We'd like to learn our treatment status and our observations. But we also have like some knowledge about how the system evolves on its own through, say, like time and space seasonal factors. An important thing is that if this effect is relatively weak, which most of our treatments are weak relative to the noise, that we need to kind of like figure out how to make the variance of the error term as small as possible. It's very common in A/B testing to do variance reduction, and you'll see methods like QPED or covariate adjustment. This is a generalization of covariate adjustment. If we have a good baseline model that can explain a lot of variation and shrink the variance of the error term, then that's going to provide us with a much cleaner estimate of the effect of the model. And so a big curve that we'd like to fit is just what would likely happen in this marketplace using only exogenous features. You can kind of see that what we care about is that the treatment does not cause X in any way. So if it does, then it's going to tend to create a bias in our measurement of the effect. So we sort of like, we need this ignorability, like the treatment cannot have any effect on this particular baseline model. So these need to be things that are kind of like totally exogenous. So things like weather or seasonality and even demand are relatively exogenous to the things that we do. And so we can include them in this baseline model and get smaller variants of the error term and be able to kind of get a more precise estimate of the effects of the treatments that we create. Okay, so I threw a lot at you here, and I think like, but at the end of the day, I haven't shown you anything that's really groundbreaking. It's just sort of like, we're still in a world of like on Pearl's ladder of just the intervention side. And it's because all I've shown you how to do is how to estimate what happens when we do a certain space-time treatment. Sort of like, well, we still have to try it. We still have to intervene, and interventions, like if we just had to like try things one at a time and wait for these experiments to run and analyze them every time, we'd be in a very slow feedback loop where we have no ability to sort of like get up to rung 3 where we can kind of imagine other things that we could be doing that we haven't tried before. So this intervention world is actually like a big step up in a lot of ways, and getting variance reduction to the point where we can make clean decisions about which policies are good ones is an important step. But the ideal is to get to the point where we can generate policies that are likely to work better than anything we've tested before without having to test them. And I think that we're working on this, and I think it's possible, and it's for what I think is a fairly interesting reason. Our policy space are functions, as we described earlier. So we have pricing, for instance, would take a session where it says the user wants to go from A to B and give it a price. So this policy would assign that $7, and there'd be like this, list of sessions and a list of prices is a way of representing a function. It's just like a lookup table. And here's another policy which charges more for that particular session. And in the middle of them, we have many other policies. And this high dimensional representation is probably can be easily approximated by a low dimensional representation. In the case of prices, you could picture just one dimension of this embedded space might just be like level of price, which is how expensive or cheap is a lift. Other dimensions of the embedded space might be like the geography with which we charge premia, or the times of days in which we charge premia. And so there's a low dimensional representation of this function that we're using in order to run our marketplace. You can do the same thing for the score function for dispatch, and the same thing for the ETA predictions, is that like on a similar set of observations, do these functions tend to produce similar values of the policy of the functions that drive our marketplace. And so there is some local smoothness here, because these policies tend to even though they might be different functions, they result in similar behavior of the marketplace. And so we should expect two policies that have very similar functions to generate very similar behavior in our marketplace. This is a powerful idea because it allows us to generalize in some ways across this really high dimensional policy space. And so we don't have to try everything. We just have to hill climb in this policy space to better policies. So I'm directly talking about Bayesian optimization here, and I'm going to do a pretty bad and cursory job of explaining Bayesian optimization. But roughly, you can think about policy 1 and policy 2, and outcome 1 and outcome 2. And we may have run an experiment where we got sort of like policy 1 improves outcome 2, but lowers outcome 1. And so we can run this experiment directly and get these experimental results. What I'm suggesting is that these policies, since they have a latent representation, which is low dimensional, that there is a smooth interpolation between them, and we should expect policies that are sort of in between these two policies to give outcomes that are sort of in between those two outcomes. This is a big assumption, but it's testable. This local smoothness of the outcomes in the policy space is a powerful tool, because now we're back to curve fitting again. If we can fit this curve, we can actually make predictions about policies that we've never run in production before. Typically, this is something like a Gaussian process that can provide like an upper or lower confidence limit on what we would like to, what we may be able to achieve under certain policies. This is also similar in a lot of ways to what people would call off-policy evaluation. So can I estimate the effects of policies that I never ran in my marketplace before? And the answer is yes. It just depends on sort of like how closely this function approximation tends to concord with what actually happens in reality, and how much variance you're able to reduce in the estimates of the effects. So we can propose a new policy and then test it, and that makes this local smoothness assumption testable. And so, you know, because our policy space are functions, they actually have a sort of nice algebra to them. So like we could just like average these two policies and say like what happens when we ship a hybrid of these two things. And we can run that experiment, or we can, in order to maybe generate a candidate that could, because of the upper bound for outcome 1 was higher under this like hybrid policy, we might try that because it has some upside and generate a new idea about how to do things. So now exploring this low dimensional policy space gives us some leverage of being able to say like past experiments that we ran are all informative about new experiments, because what we're doing in the underlying algorithms isn't that different from what we've done historically. So yet another example of like, once we can intervene in the system cheaply, it just becomes curve fitting. It's just that now instead of treatments, these are actually functions. They're not binary treatments, they're functions, and those functions have sort of like a low dimensional representation under which we can assume some local smoothness. All right, so I threw a lot at you. I think this was meant to be sort of like more of an overview and then an in-depth thing. And I hope it generated some interesting ideas and helped sort of explain the way that I've come to understand how we do experimentation and causal inference at a place like Lyft. First of all, we use experiments all the time, and in two main ways. One is to improve the underlying models, and the second one is to evaluate policies and generate ideas for new policies. The line between these two things is very blurry in some ways because we can model the policies themselves. But at the end of the day, experiments are sort of a ubiquitous tool that we're employing at all times in order to improve the marketplace. We need to fit flexible causal models that use experimental data in order to have the causal interpretation that we need, and also have contextual variation in order to explain like how that effect would vary under different circumstances, and have low variance. So a lot of the work that we're doing in these two pieces here are basically machine learning tasks where we're trying to explain either nuisance variation or explain contextual effects and generate a very low bias estimate of what's likely to happen when we do something. And that these models can be improved either through better models, better features, or through better experiments. And then finally, once we have models like this, the optimization becomes like fairly straightforward, given that we're able to make the appropriate trade-offs. So it's actually like a nice clean separation is here, is that if you have a utility function and you have these models that predict counterfactuals very well, then the optimization can become like a fairly straightforward problem, and you can kind of like make a reasoned trade-off between all the outcomes that you care about. All right, with that, I'm going to conclude, and I think there should be plenty of time for questions.